So in this section we want to learn whether a given force is conservative or not. So let's try to define what conservative forces are. So force F acting at the same material point same material point is called conservative if the work done by it from time t1 to t2 during motion of its point of application from R1 to R2 is independent path C1 connecting these locations. So if you have, say, a frame F, okay, and then you have this region R, okay, region R, and you have 2 points measured from O. One is R1, the other is R2. Okay. Now if you have this path C1 connecting the points R1 and R2. So force F acting at the same material point is called conservative if the work done by it from time t1 to t2 during motion of its point of application from R1, okay, from R1 to R2 is independent of the path C1. Okay, so if this work done, let's write W1 to 2 for time t1 to t2, and the work done would be F dot V. So this is essentially the power of the point of application of force. Okay, now this is for a given C1, R1, R2 is F dot TR for all C1 and for all R1 comma R2. So essentially it only depends on the position, okay, position coordinate, not the path locations. And this is true in the region R in which F is defined. So R may be whole of space or a part of it. So a force can be conservative not perhaps in the whole space but a part of it. That is also fine as long as you define clearly that the force is conservative in the region R and you define what the region is, it should be okay. So this also implies that this force will only be dependent on the position of the material point at which it acts, and does not depend on the velocity and time. Okay, or let me put it, does not depend explicitly on velocity and time. Okay, so let's take up an example of a frictional force is non-conservative. Okay, let's see why, just based on this definition. Okay, because its direction, since force is a vector, we have to also consider its direction. So the direction of a frictional force is velocity dependent. In case of dry friction, okay, you know that you see the relative velocity of the point of application and then decide in which direction the friction should act. So the direction of this friction force depends on the velocity. So it clearly violates this part, that it should not explicitly depend on velocity. Okay, and even in, say, the other case, so its magnitude and direction are velocity dependent if a lubricating film is present. Okay, so for example, if these are this is, like, say, surface 1, this is surface 2, okay, and then there is this lubricating film between them. Okay, so you can have, say, the velocity of each layer of it can be different from the other. Okay, and viscosity is one reason where the magnitude over here will be different than the magnitude over here. So many times the velocity boundary layers are formed, okay, in which case the velocity at this end of the lubricating film will be different than this end, because each of these internal layers will have friction between them. So perhaps this is something which need not be understood in detail at this moment. Anytime you learn fluid mechanics, I think this will present itself in a more better form. So as of now, you can just know that the magnitude and direction are dependent if the lubricating film is present between two surfaces. Okay. So the magnitude of friction at this end and this end will be different. Okay. So we draw the following inferences. Hold. This is about the conservative force, of course. So this was equation 2.77. Perhaps I didn't write that. Equation 2.77. So equation 2.77 implies that integrand is a perfect differential. So perfect differential of a position dependent single valued function. Okay, this is called the potential energy. This is the first time we are defining this. Okay, we have defined the kinetic energy, and this is earlier, and now this we are defining the potential energy. So this integrand, okay, this is a perfect differential, sorry, this one, okay, this is a perfect differential of the position dependent single valued function V of r. So capital V of r is the potential energy, and from 2.77 you can write, just by differentiating this, you can write F dot dr. Okay, you know that if you integrate it from 1 to 2, you will be able to get to this form. Okay, this form you will be able to get if you integrate it. So this particular thing is called minus dv. So v here is capital. Okay, in 2.77 we had a small v, that was a velocity and that was a vector. This one is a scalar quantity. So this implies if you integrate from 1 to 2 minus of v of r1 v of r2, okay, because it depends, as you know, only on the position. It's a single valued function, so one position will mean one potential energy only, and this is dv, and this is v of r2 minus of v of r1. Okay, so this implies the work done from r1 to r2 equals the negative of the change in v. Okay, now the negative sign which you see over here, okay, which also obviously comes up over here, is just a convention which we use, because in the, say, let's show that equation over here. Let me see that equation if I can find it. So look at equation 2.57. okay, please go back and check this equation, check the derivation. So it says that TC2 minus TC1 is equal to W star 1 to 2. Okay, now if so, the negative sign over here, okay, this ensures that if you have, say, work done by conservative force is on this side, left side, then you will can say that it's the sum of kinetic energy and potential energy. Okay, so because if you will say write this W star 1 by 2 and then separately write the say work done by conservative forces, okay, conservative, so you will have a minus of delta V, and this minus of delta V will come to plus of delta V over here. So kinetic energy plus potential energy will be equal to the work done. So just to get this sort of difference. On the left hand side you have the summation of kinetic and potential energy, and on the right hand side you have the work you do this. Okay, if you don't do this, then you will start seeing this as a difference of kinetic energy and potential energy. If this is like a Ke minus delta V on the left hand side. So, okay, so just to avoid this we do it. So it's just a fair convention, doesn't really mean anything over here. Okay, the important point to note is that V will only depend on R. It's a single valued function. Okay, now if you say take up F R2 equal to R1, okay, so if for some reason you start off with this point R1 and then take across this path C1 and then come back over here, that's R2. Okay, and it's the same point. So based on equation 2.79, you will say that V of R2 is equal to V of R1 because it's a single valued function, so it can only have one potential energy. So this implies that work done, this implies, I say, equation 2.79, work done by conservative force in any closed path C, okay, where R2 is equal to R1 is 0. So it comes from this. Okay, now let's take the third one. Let R naught be the datum for V. Datum meaning the potential energy at R naught is assumed to be 0. Okay, so this is some sort of a reference. So V of R naught is equal to 0. Now if you look at equation 2.78, okay, over here, just remove this, you have equation 2.78. you can write that V of, equation 2.78, just integrate that and we should get V of R minus V of 0, which is 0, is equal to minus of R0 R. Okay, so this is 2.80. Okay, so the potential energy at a given position, so the potential energy at a given position R equals the negative of the work done from the datum to this position and also equals the potential or the actual work done from R to datum. Just because this negative sign, you have to say like that this is a work done from R to the datum. Okay, so that's the word perhaps with the potential energy. I mean, it has the potential to do so much of work. Perhaps that's this language part of it. So if the forces are changing, then you can choose the datum, say at some place where the force is 0. That comes by experience as we go along. So the fourth point would be that if we write F dot dr is equal to minus of dv, okay, and we want to write it all in the, say, Cartesian coordinate. So F, as you know, will be fxi hat. Let me just write it once over here. So F as a vector would be fxi hat plus fyj hat plus fzk hat dr, or just r, any position, will be equal to xi hat plus yj hat plus zk hat, and clearly dr will be dxi hat plus dyj hat plus dzk hat, just because di hat and dj hat and dk hat will all be 0. So this in reality should have 6 terms once you differentiate this, but those terms would be 0. So we write this dot product as fx dx plus fy dy plus fz dz is equal to minus dv, but again dv can also be written as, so if there is a so-called total derivative of v, so it will be first along the x direction, then along the y direction, sorry, and then along the z direction. Okay, so this would be written as minus of dou v by dou x dx plus dou v by dou y into dy minus dou v by dou z into dz for all dx, dy, dz. Okay, so this is the Cartesian form of it in the Cartesian components, and if you sort of this combine now, you can say match the coefficients of dx, match the coefficients of dy, so you will get, say, fx is equal to minus dou v by dou x. Similarly, fy will be equal to minus dou v by dou y, and fz is equal to minus dou v by dou z. So the coefficients of dx, dy and dz have to be the same. And why do all the coefficients have to be same? Because this is true for all values of dx, dy, dz. Okay, since this is true for all values of dx, dy, dz, the only possibility is that the coefficients on the left and the right hand side should be matching. Okay, or in other words, fx plus dou v by dou x into dx plus fy plus dou v by dou y into dy plus fz plus dou v by dou z into dz is equal to 0. So if this is 0 for all values of dx, dy, dz, the only possibility is that these all three brackets are also individually 0. So that's the reason we are able to write it like that. Now, so if you want to say write this force like this, so please use this. Okay, F is equal to, what is Fx? It is minus dou v by dou x, that is I hat then you have minus dou v by dou y into j hat, and then you have a minus of dou v by dou z to k hat. This is f, and this is equal to minus of, I'm writing this term like this. Okay, some people also show a vector sign. I will not be doing that. Okay, now this is called gradient of v. Okay, without the minus sign. Okay, this is called the gradient of v. So this implies that the gradient of v is actually equal to dou v by dou x into I hat plus dou v by dou x dou y into j hat plus dou v by dou z into k hat. Okay. Okay. So one of the things which you should note is that the gradient of a scalar is a vector. Perhaps that's why some people do it like this. I am not doing it. Okay, it should be obvious that this refers to a gradient. Okay, so if f is conservative, then f is equal to minus gradient of v, this one. And how did it come? It came because of this. Okay, this was only true for a conservative force. Reverse is not true. Meaning if f satisfies this, then it does not mean that f is conservative. We have an example. So if v is equal to f naught x cos omega t, okay, it's a potential function v. Okay, so we are not calling it as a potential energy as of yet. Okay, but we have some v which is a scalar quantity, and now the f of it will be minus of, okay, minus of gradient of v. This gives minus of f naught cos omega t I hat. Okay, so this is not conservative, as it depends explicitly on time. And remember, we had earlier said that a conservative force acts on the same material point of the body and does not depend explicitly on velocity and time. So we cannot have this as a conservative force. So the reverse is not true for this case. Okay. Now let's take a case for any dr along a contour surface v of x comma y comma z is constant, So the potential energy, being dependent on the positions only, as it should, is a constant. Okay, so let me try to show that. You have x, y and z. Okay, now take up, say, one, oh sorry, draw a bigger diagram, I think. Okay, so say for a path like this, okay, x, y, z keep on changing themselves, but always do it in a way such that the potential energy remains the same. So it's a contour surface over here. Okay, so let's take up one path of it, one point of it, say r, and this small distance would be dr. Okay, and the force which acts over here is F of r. Okay, and say this is V equal to C2, and then you can have a third one, sorry, this is V equal to C3, and then you can have, say, a first one which is V equal to C1. So clearly C3 is greater than C2 is greater than C1. Okay, now for any dr along a contour surface V, so this is V equal to C2 contour surface on which we have taken a dr. Okay, we can write that dV is equal to dou V by dou x into dx plus dou V by dou y into dy plus dou V by dou z into dz. Okay, now this means that the gradient of V dot dr, so the gradient of V will be a vector, hence I am not showing it with a vector sign over here. Okay, this is a vector quantity, this is equal to 0. Okay, the reason is that the potential energy will not be changing with this F dot dr. Okay, because even when you go over here, the V will not change, and hence this work done would be equal to 0. Okay, so if this is equal to 0, this, if a dot product is 0, then you know that this is perpendicular to dr for all dr, and this means that F is equal to minus is along normal to contour surface of V. In the direction of decreasing V. Okay, so because it is a negative sign, so it means it's in the direction of a decreasing V. Okay, now a similar expression like what we have done over here can be done for say the cylindrical and the path coordinates as well. Okay, so for the cylindrical coordinate, and let me write that in red so that you know that you have to derive this. cylindrical coordinate system, you will have an Fr is equal to minus dou v by dou r, F phi is equal to minus of 1 by r dou v by dou phi, and Fz is equal to minus dou v by dou z. Minus dou v by dou s is the path coordinates. This all is 2.82. So please derive this in red. Okay, you have to follow the same steps which I have done. Look up how the forces and the work was written in the cylindrical and path coordinates, and then find it. Okay, please don't skip this part. You should in fact pause the video before you move ahead. Okay, so the force component Fe in the direction E is obtained. So if you have Fe, that will clearly be F dot E, and this would be minus of delta V dot E. This is the minus of directional derivative of V along E. Okay, so E may be ijk or some combination thereof, so E can be any direction. So this is something which you should keep in mind of a directional derivative of V. So if F is conservative, then the curl is equal to 0. So the curl will be equal to 0 if it's conservative, and let me show that now. So if you have the curl, this can be written as I hat, j hat, k hat, dou by dou x, dou by dou y, dou by dou z, fx, fy, fz. Okay, now this can be written as dou f z by dou y minus dou f y by dou z. I hat plus the other two terms in j and k. Okay, I'm not separately writing. Okay, well, let me just write it like this: j hat plus k hat. Now this particular term first, using this fz. So fz, if you remember, was minus dou v by dou z. Okay, so this should be written as minus of dou v by dou z. Then again you have a derivative by y, and this would be fy would be minus of dou v by dou y. So this would be plus of dou 2v by dou y dou z. I hat plus j hat plus k hat. Now the order of differentiation does not matter, and hence these two quantities would cancel each other out. So this would become 0 plus 0 plus 0, so it would be 0 overall. Okay, so this is the proof that if f is conservative, this is true. And where is the conservative part coming in? In trying to write fz as dou v by dou z or fy as dou v by dou y. Okay, so in the cylindrical part also you can proceed. Let me put that in red. The curl in the cylindrical part would be 1 by r e phi by r e z. 2 by 2z r or f phi f z. Okay, this is 2.83. Okay, now we want somewhat of a condition to check whether a given force is conservative. Okay, so 7 is, it's the last so-called inference about this. So the following theorem is to check if a given force is conservative. So if the curl of f is equal to 0 in the region R of the definition of f, then f is conservative in every simply connected subregion R1 of R, provided f does not explicitly depend on velocity and time. Velocity and time. So if the curl of f is 0 in the region R of the definition of f, then f is conservative in every simply connected subregion R1 of R, provided f does not explicitly depend on velocity and time. So let's try to understand this. So you have, say, okay, and so this is the region R. This is the region R1, which is a subset of R. Okay, and you have this curve C shown. This has an area A. Okay, a small area dA, and that would be dA equal to dA into n hat. N hat is the normal, so clearly n hat is perpendicular to dA. Okay, so it's the normal surface. Now consider a closed path C in the region R1. Okay, apply Stokes theorem. So if you do not know at this time what Stokes theorem is, you can just take it without proof. Okay, it's very commonly used in fluid mechanics where you want to convert, say, the volume integral to the surface integral, or a surface integral to a line integral, and so on. So the work done is equal to this whole loop, okay, the C and F dot dr. Nothing wrong in this, okay, it's a closed loop C. Now you are applying the Stokes theorem and writing this line integral as a area integral, okay, and that will come using this curl dot dA, okay, and this will be equal to 0. This will be equal to 0 because the potential energy at initial and this ending point is 0. So the work done has to be 0. Okay, so this is there. So this is equal to 0 where A is any surface area in R1 whose bounding surface is C. Okay, so because this force is conservative in this is equal to 0 because this is equal to 0, okay, and this is 0 because of the earlier point which we have just made. So this force, the curl of this force will be 0 in the region R, hence it will also be 0 in the region small r, R1, and that's why this particular integral is equal to 0, and that proves eventually that force is conservative. So one way or the other you can look at it. Now let's come to the simply connected part. I mean, that's what somewhat worries us. This is some of a new word over here. Okay, if this is equal to 0 in the region R of the definition, then F is conservative in every simply connected region R1 of R, provided F does not explicitly depend on velocity and time. Okay, so let's take up, say, consider a planar force, okay, and this work to run will be also to 0. So you can see either ways, basically you can see in either directions, okay, either from the work or this curl, both of them. Now consider a planar force field F is equal to C by R E phi hat. Okay, this is not defined for R equal to 0. See, eventually we want to calculate the curl, okay, and we are not defining it for R equal to 0 in this cylindrical coordinate because you have this 1 by R and 1 by R over here. So you don't want to define it for R equal to 0, otherwise it will blow off. so you will not be able to write the curl. Okay, so the curl of f, okay, using equation 2.83 which we have just seen and read, this should be equal to 0 by r er plus ez. This is equal to 0 for r not equal to 0. So the curl is 0 definitely. Okay, and let's now consider a region R1. Okay, this is O. Okay, and say you have a loop, two loops. Let's draw. One is this C1, okay, the other can be this C2, okay, this is region R1 clearly. Okay, so this should be, oops, this is R1. Okay, now this is a planar force. Okay, you have calculated the curve. This is the region R1. Okay, clearly it's not defined at r equal to 0, so we are not like getting into this special point. Okay, r equal to 0. Now this curl is equal to 0 for all values of r not equal to 0 in the doubly connected region R1. Okay, it is not simply connected because I think we should tell a definition now. Now simply connected, say in a planar situation, is something like this. Okay, it's simply connected because you can calculate any loop like this and shrink it to a point. Okay, if you shrink it to a point, then you will not be leaving the solid anywhere. Okay, so you will always be within the solid as you shrink this loop. On the other hand, consider this with a hole. Okay, now if you sort of draw a loop like this, okay, and try to shrink it, there will be a part of it which will definitely be lying outside the solid because this is a hole. Okay, this is not a simply connected solid. This is a simply connected solid, not a simply connected solid. Okay, so that's why we are calling this particular solid, because this is a hole for you. Okay, this is a hole, so that's why it's called a doubly connected region R1, not a simply connected region. Okay, so that we are just trying to study the importance of the word simply connected in the definition. So this is true in the doubly connected region R1 in the xy plane. Okay, so for this one you have phi over this C1 path. Okay, you can see the C1 green color, and that is f dot dr will be equal to, say, 0 to 2 pi, because you are going from 0 to phi. That will be c d phi. Okay, because you have f equal to c by r e phi. Okay, now this comes out as c d phi, and this value will be equal to 2 pi c, which is not equal to 0. So c is not equal to 0, because if c is equal to 0, then this force is equal to 0, which is not. So let me write that here as well. C is not equal to 0. Okay, so this is not equal to 0 for curves like C1, which enclose the hole. Okay, remember, if it was a simply connected region, this quantity should have been 0, right? It was earlier 0 over here, f dot dr over a loop. So this is not 0 in this particular situation. Okay, and this implies that force is non-conservative in R1. Okay, now you can always say, well, there was also this C2 which we could have looked at, and then if we had performed this integration we would have got this. Now the key is that if you are defining a whole region R, this definition which I have told you, that you should be able to draw a loop and you should be able to shrink it, should be true for any loop. Okay, not just specific loops like the C2. So it has to be for any and every loop which can be drawn in this region. Yes, it is true that if you were considering this as a separate region, okay, like R2, and then you could have said that this R2 may, this F is conservative, because you can draw a simply connected region and this integral would have been equal to 0. Okay, so let me just, okay. Fine. So once we show that force is non-conservative in this shown region of R1, because it was clearly not simply connected. Okay. So not simply, R1 is not simply connected. So this simply and multiply connected comes from topology, and this definition which I am telling you about a loop being, you being able to shrink it without leaving the solid, is somewhat of an informal definition, but it works reasonably well. Okay, so in this case the potential would be, so if F is this, okay, my C by R E phi, then the potential would be minus of C phi. Okay, and this is multi-valued in R1. Why is it multi-valued? See, take up something like this. Okay, say this angle is phi, x and y. Now you keep on adding 2 pi, you come back to the same, so this will be phi plus 2 pi, and you are at the same angular position. So if it were single valued function, then you should have the same value of v of phi and v of phi plus 2 pi. But since this is a non-conservative force, this v will not be single valued, it will be a multi-valued function. Okay, and that would imply that v of r comma phi comma z is equal to minus of c phi, it will be minus of c of phi plus 2 pi, and it will be minus of c of phi plus 4 pi, and so on. So the single valuedness is lost over here, just because it's a non-conservative force. Okay. And that is just because you are still in this region R1. Okay. So your phi is being still measured with respect to this O, part of it body is. So even though you are considering the loop C2, as long as you are in R1, you still have this problem. So this phi is measured like this. Okay. Okay. Now, if you somehow have a situation like okay, if you somehow have this situation in which, so I have already discussed that in this region C2, W will be equal to 0. Okay, so if you have this region C2, W will be, say if you follow a loop, this will be equal to, work done will be equal to 0. But of course it's not a, the whole region is not simply connected, and hence this force will not be conservative. So despite the fact that W is 0, the force F is not conservative in this region R1. Now how to get around this problem? If you have, say, a simply connected, or sorry, a multiply connected region like this, okay, just like, so you have a hole like this, you can make it, you can modify its geometry in this way. Let me see. So okay, so this green is this new surface which you have, something like this. Okay, this is a modified to simply connected. Why? Because any loop which you draw on this one, okay, originally in the solid, say something like this. Okay, now if you keep on shrinking this loop, okay, keep on shrinking this loop, you will always be within the solid. So this is modified to be a simply connected region. So this is R2, okay. So in this case, F will be conservative. Okay. So that's the importance of this word simply connected in this theorem. So I hope both of these two things are clear with all of us over here. Okay. So in this topic we will just try to find out the potential energies due to some conservative forces. So this is sort of like an example building exercise. Okay. So we'll take up some examples of a conservative force and then try to build up the potential energy. Okay. It's mostly about choosing the path along which the integration has to be performed. So you recall that potential energy is equal to minus of R0 R. So R0 is the datum point where the potential energy is 0. Okay. So let's try to see a example. Say you have Y, you have X, you have Z, okay, and then you have this point B, you have this point A, you have this point D. Okay, so you have the angle phi. Okay, fine. So let's try to see this curve C1, which is OABD. OABD, okay. And let's take another curve. I'll perhaps show it in a different color. C2, which is OBD. So that will be OB and then up to D. Okay. So let's try to do this over first C1. VR minus V0, because O is 0 vector, it's the origin. And this is C1 going from 0 to R. F dot dr. Now if you take the dot product f dot dr, one should get along the x-axis. So first you want to go from 0 to a, that will be only a translation along the x-axis, okay, and then one should go from a to b, that will be a translation along the y-axis, and then going from p to t, that will be a translation along the z. So I think I should call this as I hat. Let me just show this as the direction, j hat and k hat. So fx would be x comma 0 comma 0 dx minus 0 to y fy 0 comma y comma 0 dy minus 0 to z fz I'm sorry, this should not be 0 comma y because there is already an x, even though it is fixed, okay. When you go from a to b, you already have a fixed x, okay, and obviously what is changing over here is not x but only y, so that's why you have a y. Similarly, when you are at the point b, you already have a x and a y, and the z will be changing, and hence the integration is performed over that, okay. So this is how we would get Vr minus V0. Similarly, this quantity is to be calculated over C2, going from 0 to same position, okay, f dot dr. Now going from O to B, that would be at a constant phi but changing r, okay. So going from O to B, it's a path which has a constant phi but changing r. So I'll write it as fr r phi 0 dr. And then going from B to D, it's a constant r and phi, but the z is changing. So it would be r phi z dz. Okay, so this is 2.85. Now this is how you have calculated the potential energy, say for a piecewise linear curve. Let's take up another example. I mean, in this case itself, so let's call it example 2, but it's somewhat related to this case. So for example, if the force has components fx, fy and fz, over here fx, fy and fz can depend on all three coordinates, meaning x, y and z. But if for some reason they are only dependent on, fx is only dependent on x, fy is only dependent on y, plus fz is only dependent on z, okay, then we can write this quantity as 0 to x. So we'll just use this expression 2.84 equation. Over here it will just be f of x dx minus 0 to y f of y dy minus 0 to z f of z dz. Okay, this is 2.86. And in a specialized case where f depends, say, only on fx, okay, there is the Fy and Fz are 0, then automatically you would have Vr minus V0. Actually, I should not be writing V of 0 every time because that is 0. But anyways, so this can just be written like this. Okay, and a further specialization is if F is constant. Okay, so that way we will have Vr minus V of 0. This quantity is anyway 0, these are all zeros. This is equal to minus of F dot R, or minus of Fx x minus of Fy y minus of Fz z. This is 2.87. Okay. Now let's take another case which affects all of us. Let's call it, I'll just call it the x-axis in the I direction, y-axis in the j direction, and z-axis in the k direction. So if you have something like this, it's C is the center of mass, dm is the small mass of it. Okay, force acting on this small mass is minus of g dm k hat. And this is the datum plane. Through O, meaning the potential energy anywhere on this plane is 0. So this, I think I should draw this as a slightly bigger plane. This is called ZC, Z coordinate of the center of mass. This is called Z. Okay, so this is at a height of Z from this particular plane. Okay, so now we were talking just about F being constant. So if you have a uniform gravitational field, okay, so the potential energy, so the force over here is clearly minus of g dm into k hat, or let's say df, small force is like this. Okay, and the total force would be minus of gm k hat. Now the potential energy due to this, just use equation 2.87, is not 2.87, I'm sorry, you have to do the whole integration. Okay, something like this. So you have to do it g of z m g z dm. This is equal to mg zc, because the integration of, okay, this integration should give you this value. Okay, so this integration essentially gives you the center of mass. So zc is what you get. Okay, now let's move ahead and take up one more example. So let's see, you have x have y, you have z. This is a frame F. Okay, and A, and this is say P. This angle is theta at T1. Now before this T1 there was a time T at which so it's the same body, okay, it doesn't really look like that, but so at this point Q you have this couple moment, you have A and you have B, theta of T. Okay. Equal to theta dot k hat, and say as a third some other time between A and B, this theta of T2. Okay, now if you have a constant moment, we want to find the work done by constant moment or couple moment C. Okay, it is acting at Q of a rigid body, and that rigid body has a angular, it rotates with this omega t as omega t k hat or theta dot t k hat. Since it's a rigid body, we can just draw this line between A and B and track how it's rotating. Okay, so theta at T1 to theta at T2. So you want to calculate basically the work done between these two instances, T1 and T2. So let's see how we can do that. T1 to T2, this dot omega T tt, this would be the work done. Okay, just like you have F dot dr, where you can have a C dot omega dt. Now if C is constant, it can be taken out and the integration will be, so this value is actually only theta dot. Okay, this is theta dot, so that integration can be done and you can write theta of T2 minus theta of T1 into k hat. Okay, this from this is what we are using. Okay, now you want to write, so C is acting at point Q. So if you take this particular dot product, that this essentially means you are just resolving the C along the Z axis. So that would mean you have Cz theta of T2 minus theta of T1. Okay, so yeah, this is equation 1. Now this W is independent of path. Okay, so it only depends on what is the position theta at T1 and position theta at T2. independent of the path followed by the body from its initial configuration to its final configuration. So what does this imply? It says something about this constant moment C. A constant moment acting on a rigid body moving with angular velocity having only z component is conservative. And with the potential energy as minus of cz theta. Clearly at theta is equal to 0, v is equal to 0, so that's the datum. But if omega is arbitrary, yeah, it's supposed to have a direction component only in the z direction like it was in this case, then it's a conservative force. But if omega is arbitrary, okay, then it's non-conservative, because in that case the work done will be dependent on the path. Okay. Okay, so if you have, say, now a seventh point would be, if you have a for a pair of mutual central forces F1 and F2 with F1 minus F2 is, say, equal to F1 ER hat or F of R comma theta comma Z, R comma theta. Okay, so let me just use the cylindrical coordinate as an exception. We don't do this in this course, but over here it seems I don't have much choice. So let me just do this. You have frame F. You have F2. You have F1. Then you have this O over here. This is okay, it shouldn't come like this. This is R1. Similarly, you have R2. Okay, and then this vector is r. This is body 1, this is body 2, and this is the direction ER. Okay. So for a pair of mutual central forces F1 and F2 with F1 equal to minus of F2 is equal to F1 ER, okay, we can write dW is equal to F1 dot dr1 plus F2 dot dr2 F1 dot, so we can just take this minus this one, okay, and then we will have a dr1 minus r2, okay. This value can be written as equal to F1 ER hat dot dr. Now this dot dr, so this dr in the cylindrical coordinate, okay, we can write this as dr er hat plus r d theta e theta hat plus r sin theta d phi e phi. F of r theta phi. Okay, so if you do not, if spherical coordinate is not something which one has done, you can just ignore this particular line, okay, it's okay. So you have this dr, so this force will be conservative if f of r theta phi is equal to fr, because only in that case this integration, if you do, will depend only on r, okay. If it still depends on theta and phi, then it's not exactly conservative. So the potential energy will be equal to if in this case, for example, you have this point 2, okay, this point 2, if this is fixed, okay, then the work done by force F2 will be equal to 0, and this equation in that case will only be giving the potential energy due to the single central force, which is F1, okay, so that in itself will be conservative. Okay, now you have already done this before, but I will write out just the answers. If you have, say, a gravitational force minus gmm by r square, then the potential energy should be equal to minus gmm by r. Please do this and do not skip this. Datum over here is r naught tending to infinity. So at infinity the potential energy is assumed to be 0. Similarly, you have, say, electrostatic force, which is Fr is equal to Q1 Q2 by 4 pi epsilon naught square. We have seen this before when we learned about the electrostatic force in electrostatic field. Okay, so if you have 2-point charges Q1 and Q2, this is a force between them. The potential again would be Q1 Q2 by 4 pi epsilon r square. Okay, datum is again at infinity. Second, you may have, say, an ideal elastic spring. When we say ideal, it means that the spring itself is massless. Inertia is negligible. So this one, actually, let me do this. So if we have, say, two bodies which are this is R1, okay, and this is the separation between the two. So this is O. Now just take the spring out separately. So this is 1, this is 2, F of E of E, and the two bodies which are there, say this B1 and B2, they will experience this force 2 over here. This is F of E. This will experience 1, will experience a force again F of E. This is body 1, this is body 2. So it's an ideal spring, and this ideal spring is a two force member. Please go back and revise this concept if you do not recall it. It's a good time to pause the video and revise what a two force member is and what does it imply. Okay, so the forces at ends must be equal and opposite only if it's an inertia-less spring, ideal spring. Okay, and act along the line joining, which is ER. When we say an elastic spring, it means that if you remove the end loads, it will come back to its original undeformed state. So if L0 is the unstretched length, so let me just draw a few graphs because we'll be referring to it. So this is the force versus extension graph. Okay, so clearly the force over here is sort of varying non-linearly with the extension. You can also have a situation in which the force in the spring is F equal to Ke, meaning a linear variation. So this would be dE, and V of E will be equal to half K E square. Okay, now if the pull on the spring is Fe for an extension R minus L naught, okay, R, if you remember, is the separation between the two ends of the spring, okay, and if L naught is the unstretched length, the extension will be equal to R minus L naught, okay, and F of E is the pull for this given extension. So Fr is equal to minus of F of E. This implies that dE will be equal to dr, because L naught is undeformed, so it's a constant. Now if you use equation 2.88, this equation, just put F of R over here and dr as equal to dE, one would get VE is equal to 0 to E F of E dE, okay, and the datum is clearly the unstretched, meaning E equal to 0 is the datum. So this particular integral FED gives you actually the area under a curve over here. So if you have a generic F of E, this integral will give you the area under the curve, and it's also the potential energy of a spring in this case. Say if you have something like this, you have body 1, sorry, it should be a spring. You have body 1, body 2, so this value of VE equal to 0 to E F of E dE is also the potential energy of a central spring force F is equal to minus of F of E ER acting on body B1 with the other end. fixed. Okay, so this is fixed, this body too. Okay, this is fixed. So it will also give the potential energy of a central spring F is equal to this one acting on a body B1. So clearly this ER will be in this direction and the spring force will be of minus of FE in the opposite direction. So if you have, for example, FE is equal to K1E plus K2E cube, a non-linear one, okay, something like this. In that case, you can just put this over here and integrate it. So for this case, you will have this is equal to half K1E square plus half plus 1 by 4 K2 E4. Okay, this is equation A. If you have a linear spring of stiffness, KE, okay, linear spring is something like this where the force will depend linearly on the extension. Then you will have V is equal to half K square, okay, and where E is the extension clearly. So above expressions which you have, say this one is A, this one is B, and 2.89 is this one. So these expressions, this and this are valid even when the spring is in compression, okay. So exactly same thing will happen over here. Just that DE will now have a opposite sign, but other than that there wouldn't be any issues with it, okay. Let's take up torsional spring, okay, like the ones used in old clocks and watches, on some of the old toys as well. So I can just draw this like this. So you have this as the direction E, this is body 1, this is body 2, and you have your torsional spring over here. This is theta 2, this is theta 1, and theta is equal to theta 1 minus theta 2. So consider you have an ideal elastic torsional spring. Okay. Again, ideal means that the inertia is neglected. Elastic means that only when it is twisting it has any torque. Otherwise, it will not have it. If it's coming back after a given twist to its original position, it will not have any moment. Okay. So the end moments along the axis E. Okay, so elastic, as I've said, is the when the spring recovers its undeformed shape and size on removal of end moments, and the moment twist relation is the same during loading and unloading. So just like over here, if during the extension the force is increasing like this, during the removal of the force it should also decrease along the same line. Same for over here. Okay, it goes up like this and comes. This is elastic. Same for m versus theta graph. I am not separately showing, or let me just do that once. M t of theta. So you have something like this. Okay, and elastic means that once you remove the end loading, it will come back to zero moment using the same exact path. So okay, so over here one strip will be d phi, from here it is phi, and the area under the curve will be v of theta. Yeah. Mt is theta. So theta is equal to 0 would have mt of 0. Okay, you can see that over here. We assume something like this. Now if you have omega 1, meaning for body 1 it is omega 2 plus theta dot e, and m1 is equal to minus of mt of theta e hat to minus of m2. So the rate of work done, W dot, is equal to m1 dot omega 1 plus m2 dot omega 2. Okay, so m1 and minus m2 have to be there, otherwise the whole system will start accelerating angularly. Okay, there will be an angular acceleration. So m1 has to be equal to minus m2 for its equilibrium for the whole system. So this is the whole system. Okay, okay, so this, we don't want the spring to start accelerating, that's why m1 has to be equal to minus m2. Okay, now in this case one can write it as m1 dot omega 1 minus omega 2, this is equal to minus of mt of theta e hat dot theta dot e hat theta dot, this implies dw is equal to minus of mt of theta okay. So because this work done will not, once you integrate it from say a theta 1 to theta 2, this will only depend on the angular rotation of the spring, and hence you can say that the pair of moments together are conservative. Okay, so the potential energy in this case v of theta (2.90). Okay, so theta equal to 0 is untwisted, and this is the datum. Again, this will be the area under the curve over here. Okay, that's, we have already shown that over here. If you have a linear torsional spring, it would again look like this. Kt, by the way, would be called a torsional stiffness, and then V would be equal to half Kt theta square. Again, this is valid for both a positive twist or a negative twist, all of it. Lastly, we can see a so-called zero length linear spring. Linear spring. So if f of r is equal to f of E is equal to f of r minus L naught is almost equal to kr. Okay, if this approximation can be made, then it's called a zero length spring. Okay, so the idea is that original length of this is actually equal to 0 or very small perhaps. Okay, so if in this case the potential energy would be equal to half kr square. So this can be, say, taken in a case if you have f of f and r, and then a to b, and say the actual path is something like this. So you have this as L naught. So if r is much greater than L naught, then in A to B, Fr can be approximated as Kr in this range. So hence you must perform the integration in the given range. Okay, so this is there. So if L naught is really very small, so even if you integrate it from 0 to the final value, the answer would not be much different. So that's the idea of a zero length spring. Its initial length is not actually 0, but it's very small compared to how much finally it would extend to. Okay, so that's what a zero length spring would be. So you may have a situation that the forces are acting on a body and yet they do not do any work. So a force system like that is called a workless force system. So let me put that down in words. A force system which does no work on a body in any direction, in any motion, is called a workless force system. So we'll see through some examples that there is forces, there is definitely motion, but there is no work done. Okay. So let's take up a situation. Say you have this body 1 point A VA, then this is omega 1 R C. You have B. So you have B on another body 2. This will have a minus of R. It will have a VB. It will have a sorry, I should have C, and then you have a minus of C, and you have a omega 2. Okay, so if you have say a pair of force reactions R and minus R, okay, and moment reactions C and minus C, okay, on rigid bodies 1 and 2 at a joint or contact at A and B, okay, so then you will have a rate of work done will be equal to R dot VA minus VB plus C dot omega 1 minus omega 2. Okay, so let's take up 3 situations in which this will deliver a zero work. Okay, so let's take up case 1. So if you have a frictionless joint, okay, the joint is at A or A and B, frictionless joint, so this is VA, okay, and say let's take up this point, we'll have a minus C, we'll have a omega 2, this is body 2, we have minus R, and this is VB. Then at A we have R, we have omega 1, and then you have minus omega 2 because omega 2 is over here, so this will be minus omega 2. So this will become omega of 1 with respect to 2. Let's call this as omega into E star direction. Okay, similarly you have VA, and now VB is like this, so minus VB would be like this, and this would be VA of B to V in the direction E. Okay, this is clearly body 1. So this is how we have a frictionless joint with A of body 1 coinciding with B of body 2. Okay. Now VAB is equal to VA minus VB. Okay, this is equal to VE hat omega 1 with respect to 2 is equal to omega 1 minus omega 2. Okay, this is called omega E star. Okay, so this would imply that R okay, has no component along E. Okay, because this angle then would become equal to 90 degree. Which one? This angle. Let me show in a different color. Okay, and similarly this angle is 90 degree. Okay, so this would mean that sort of R dot E is equal to 0, and similarly C has no component along E star. E star, that would mean C dot E star is equal to 0. So for these particular joints, okay, W dot will be equal to 0, okay, because you can write it as R dot VA minus VB is equal to VE dot plus C dot omega E star. Okay, so this is 0. Okay, so this is an example of a workless force system, despite the fact that you have the reaction forces and the moments acting at the point of contact. Okay, you have a situation in which the work is not being done. So this was clearly a case of frictionless joint. So let's take up the second case. Over here, say there are two bodies in contact. So this is body 1 A, B, this is body 2, so sorry, I draw such ugly figures, so it's hard to draw the same figure again. Okay, but it is the same body, so I am now just separately showing them. So this is point A. So you have a reaction force, say R, you will have a reaction force minus R on B. Okay, so this is a point contact with no slip. VA will be equal to VB and C will be equal to 0 in this case. So that's why W dot, if you look at this one, will be equal to 0. Again a workless force system. Okay, now let's take up a smooth contact. So if this is point A, this is B, this is 1, this is 2, and this is, so VA, VB, and clearly N minus of N hat is equal to N hat A B. Okay, so if you have a smooth point contact, this can be with or without slip. C will be equal to 0, R will be equal to N star. Okay, unlike over here, because we have not said that it's smooth over here in this earlier case, so friction can be present, but over here the only force is the normal force, and that's why you have R equal to N in the direction, and so small n is the normal to the tangent plane, is normal to tangent plane at the point of contact. So W dot is equal to R dot VA minus VB. Okay, just because C is 0, this can be written as N dot VA minus VB. Now if you take a dot product with N, that would mean that you have this velocity of A dotted with N would give you the VAN component minus VBN component, and this is equal to 0. Okay, as N is equal to 0 for impending separation, okay, so the normal force will be 0 if it is just about to separate. Okay, and if it is not about to separate, then VAN will be equal to VBN for no separation. So if any of this condition is true, then this will be equal to 0. Okay, so that's why it's a workless system, force system. Okay. So there are several examples given in your textbook about workless system. I can perhaps say take a couple of them just as an example, and you should be able to do the remainder of it. Okay, so if you have a say a reaction R of a smooth ball and socket joint, okay, with a fixed body. This will be a workless force system. Let me draw that. So if you have, say, a fixed body like this is the socket, okay, and the ball is something like this. Okay, so this is fixed, this body 2 is fixed, okay, and A is the center of this ball, or the so-called point in contact. So A point is the point of contact. Now if I separately draw this, okay, there's a reaction force clearly. This will not be doing any work, this force R, okay, just because this point will not be moving anywhere, and friction will not be acting because it's a smooth ball and socket joint, so that's why it's not shown. Okay, now let's see another situation. Example, the pair reactions R and minus R on two bodies due to smooth ball and socket joint connecting them. So now the body 2 is not fixed, okay, so one of the rigid bodies is not fixed as it was in the earlier case. So let's take a situation, this is body 1, okay, so this has point of contact with body 2. So A comma B are the coinciding points. So A is belonging to body 1, B is belonging to body 2, okay, and since they are in contact right now, they are coinciding. So if I separately draw this body 2, you have this point B. I separately draw this body 1, it has a point A. If this is R, then you will have this as minus R, okay, because it's a pair reaction on this. This is also a workless system, okay, because the VA minus VB, you have to really see what happens over there. So please check with this expression why it should be a workless system. Okay, so there are several other examples of this particular form. If you have say, the last one maybe we can take is the pair of tensions in a light inextensible cable. Let's see why. So if you have this body 1, body 2, point B, body 1, point A, and then you have this E, body 2, point B. This say has a velocity of B. It has a minus TE hat. Then you have point A, TE hat, VA. So for this particular case, you have W dot as T into E dot VA minus E dot VB. Okay, so this T, this has been taken out. Okay, so this will just mean that the velocity of A in the E direction and velocity of B in the E direction. So this will be equal to 0. It will be depending on whether T is equal to 0. This is a case of impending slackness. Okay, it is just about to become slack, or along this direction E, the components of the velocities of A and B will be same. So if it's a taut, then it will be inextensible. Okay, so that's where we can end our discussion on workless force system. There are several other examples in your textbook which you should be able to verify. So verify other given examples from textbook. Okay, please do this. You should be able to figure out why is W dot 0. Okay, like over here we have these two conditions, either of them are true, it will be workless. So you have to consider all possibilities, not just one possibility. Okay, so we can also, I mean, this is somewhat of a trivial discussion, but we can do it now rather than later. The difference between a deformable body, a rigid body, or a mass point body, you know all of it, but this is just to sort of bring it all together. So if you consider, say, a deformable body, this is clearly a point where if you, a body in which if you have two given points and you apply forces on it, the separation between them will change. Okay, so that's where you call it a deformable body, and it has infinite degree of freedom. Okay, you have infinite degree of freedom of a deformable body. The reason is that you have to specify the position of every material point. So if this is a deformable body, all these infinite, and why infinite? Because in a continuum model, you can model a deformable body by infinite number of points. Okay, so they have infinite degrees of freedom because the position of every material point is to be specified, unlike in a rigid one where it's 6. We have already seen that. Okay, so in a deformable body, you apply the Euler's axiom on a small part of it. Okay, essentially the first and the second law of motion on a small part of this, and then you can sort of integrate it for the whole body. Okay. So once you apply the Euler's axiom, you will have more unknowns than the partial differential equations which this will give. Okay. So to get over that, you will have to supply some sort of additional information. Normally the relationship, say, between force and displacement, or in more advanced theories this relationship between stress and strains. Okay, but something else has to be supplied because the number of unknowns are much more over here. Okay, then you have a rigid body which we have been dealing with. That's not actually a deformable body, we have a deformable body model. Okay, a body is modeled as a deformable body, or it is modeled as a rigid body. There is no body which is actually absolutely rigid. Okay, so you know the definition that if you have this point A between these separation between these 2 points, it remains exactly like this at all times, no matter what loadings or motions it is going through. Okay, so this is a rigid body and no body is perfectly rigid, hence we make this assumption many a times depending on our situation. For example, if you have say many parts of a machine which are moving, so you can study the kinematics of it using assuming them to be a rigid body, but when you really want to understand what are the internal forces acting on it, then you have to consider them as a deformable body. Okay, so this is something which has to be understood by you, that it is a body which you are modeling either as a rigid or a deformable. It may not actually be rigid or deformable. Absolutely rigid anyways doesn't exist. The third and the last is mass point model. Okay, or the so-called particle. This is something what you have been learning before you are studying this course right now. Okay, perhaps in your school, remember everything was assumed as a uh, particle. So remember you had these two blocks perhaps kept over each other. Okay, and then you would model them this and this like a particle. Okay, if you have say some forces like that, there's friction and all sort of things happening. So you used to model this as a mass point, this as a mass point. Okay, and by doing that you were actually assuming that F is equal to ma c in the inertial frame. So the motion of the center of mass of the body is the same as that of the point body of mass m under the action of a force. Okay, so this was the idea about it, and it depends on different situations of your application of the problem, whether you can model it as a point, a mass point model, or you can model it as a rigid body, or you should model as a deformable body. So over the years you will have this experience. Okay, so one example is that if you have a mass pellet, okay, it's a very small item with a lot of mass. Okay, and then you want to center of mass of it falling in still air. This you can do using a mass point. But if you have say a leaf falling in still air, okay, you have to model is at a deformable body, because then this assumption of a leaf, because a leaf will have something like this, okay, and then different parts of it will be experiencing different forces from the air around it. Okay, and hence it will be incorrect to model this as a mass point. So you must model it as a deformable body. Okay, so depends on your application, it is exactly what you should be doing. So this is something you can perhaps read from your text. Okay, and I think the examples will be the more helpful in learning. Examples will help in learning. So this wisdom, whether to model it as a mass point or a rigid body or a deformable. So just for your information, this is something which you do it before in your school, before you move to say an engineering institution to study mechanics. This is where you are right now. Okay, and this is something which you do perhaps in the later parts, especially if you are belonging to say a mechanical or a civil or a branch like that. Okay, so you should know all of them, and depending on your experience and your understanding, you should be able to model all of them. So of course the focus of this particular course is rigid body. Okay, so we want to discuss the work energy relation for the center of mass for conservative forces, which we have just learnt about. Before we do that, there is a small sort of announcement that all statements in this section and following, as long as we are in the same topic of axioms and force systems, are in the inertial frame. Okay, so we won't be writing the symbol I, but we should be aware that they are all in the cylindrical frame, and the reason we already know is that the Euler's axioms are only valid in the inertial frame. Okay, so once this is done, let's write that WC star dot is the rate of work done by external conservative forces W star NC be the rate of work done by external non-conservative forces. Okay, and both of them are as if the forces are acting at center of mass C, because we have to write all this in terms of the center of mass, this work energy relation. Now let V star be the potential energy of this. When I say this, I mean the external conservative forces. Okay, so this would imply that WC dot star is equal to minus of V dot star. Okay, just because WC would be equal to minus of V, so a time derivative can easily be taken. So let's now check equation 2.57. Okay, let me pull that out, and you should also look for equation 2.57, and we want to invoke that over here. Okay, there you go. So equation 2.57 is T dot C is equal to W dot star. Okay, so W dot star is the rate of work done, or also called power of all external forces as if acting at C. So we want to now invoke this. This would imply that T dot C is equal to W dot star, and since this is the work done by all forces, we can separate out them into the work done by conservative forces and the rate of work done by non-conservative forces. Now the first term is equal to minus of V star, and the second term we want to write it as it is. Okay, this implies that TC dot plus V star is equal to W star NC dot. Okay, now this is also the reason, remember we had discussed why the potential energy is defined with a negative sign. Okay, over here this is done so that it can look like the sum of potential and kinetic energy on the left hand side over here. So there's a dot over here. Okay, so that's what it is. Now this would imply that if you have states 2 to 1, then you can say that Tc2 plus, I mean doing a time integration basically from time 1 to 2, T star minus Tc1 plus V1 star is equal to W star NC 1 to 2. Okay, this is equation 2.91. This also implies that if all the forces as if acting at C are conservative, then W dot NC star is equal to 0. Okay, this would automatically imply that W star NC would be equal to 0. Okay, then this would mean that T dot C plus V dot star is equal to 0, or Tc2 plus V star 2 is equal to Tc1 plus V star 1. Okay, this is 2.92. So this is the so-called work energy relation for C for conservative forces. Okay, we have just separated the total work done by all forces into work done by conservative and non-conservative one, and claim that if the non-conservative rate of work is 0, then the summation of potential and kinetic energy at two states is the same, or it is so-called conserved. Okay, we can now move on to this topic of dynamics of translating system. Let's okay, let's first define what a translating system is. A system is said to be defined to translate relative to I an inertial frame if the displacements of its material points are the same for all time. Okay, if the displacements of its material points are the same for all time. This is a translation. So you can have, for example, let me just write them separately. Let me draw a diagram actually. So this is your inertial frame, okay, and say this is your system. You have this point Q, you have this mass dm at position P, and then this has a velocity of P, this has a velocity Q. All of it is in the I frame, okay, that's why we are not separately writing all these velocities. And then you have RPQ. Okay, now we also need center of mass, say C over here. It will have a velocity of VC, okay, and say any generic point like A, it will have a velocity of A. I have a say generic point I, this has force Fi and velocity of I. Okay, this is say the M. The system is the M frame. So system is said to be defined to translate relative to I if the displacements of its material points are the same for all time. This means that the displacement of point P at time t is the same as displacement of point Q at time t. And when I say point P and Q, these are the material points of the continuum. Okay, we have learnt about the continuum hypothesis. This implies that the velocity of P is the same as velocity of Q. Okay, again all in differentiations happening in the I frame with respect to the I frame, and this also implies that the acceleration of P is the same as acceleration of Q. This implies RPQ dot is equal to VPQ dot is equal to VP minus VQ is equal to 0. Okay, this implies that this vector RPQ is a constant in time. This implies, in other words, the distance between any 2 points to any 2 material points P and Q remain constant. the system translates as a rigid system so with no change in orientation. Okay, because when we say this vector rpq is constant, it just doesn't mean that the magnitude of it is constant, the direction of it is also constant, and that's why we say that the system translates as a rigid system with no change in orientation. So no change in orientation is coming from the fact that the direction of rpq is also not changing. Okay, and all this is true irrespective if irrespective of its constitution, that is rigid or deformable. See, you can always say that the distance between 2 points say P and Q is constant in a rigid body, but we are not forcing that over here. We are coming from this definition that this system is translating with respect to an inertial frame I, okay, and that would mean that the displacements of its material points are the same. So we start from over here, then we can differentiate it with respect to time with respect to I frame, get the velocity and acceleration, and then write this vector rpq dot as the vector vpq, okay, and this can be written as vp minus vq, which is 0, and we get rpq is constant in time. So we never assumed, coming from this way, we never assumed that the system was deformable or rigid. Okay, this was never, though what we get at the end, it looks like as if the material is rigid, and that's why we say that the system translates as a rigid system with no change in orientation irrespective of its constitution. The material itself could have been deformable, but it translates like a rigid system. Okay, and the important part is that you should note the direction of how we are flowing from this side, okay, to this final conclusion. Okay, so let me write out now over here. I have this point A now. I want to write VPA and VPC, okay, and VIC. So I will write the velocity of P with respect to A, with respect to C, and then velocity of I with respect to C. So VPA is equal to Vp minus Va is equal to 0 by the same logic as before. Just like what is true for P and Q will also be true for P and A. Okay, this implies that the velocity of PC will also be 0 because C is also another point on this. So VPC will be 0, VIC will also be 0. Okay, same reason that the point I and C are just 2 points on this system. Okay, now we want to write the momentum of this system. So let's have this as mass m, okay, and Vc is the center of velocity of the center of mass. So that's how we can write the momentum. Okay, we want to write the moment of momentum about A. So H A T, this is equal to 0. Why would this be? Why would this be? You should know this, okay? Figure this out. Remember the Euler's axioms and the theory and the derivations of it. Also some extensions do this. And Hc of t will also be 0. Again, you should be able to answer why. HB we want to write in terms of HC, but anyways that is 0, so we will just write it as HC plus RCB cross MVCB. Let's see whether this checks out. Okay. Yes. Okay. So this is what you would get over here. HB is equal to HC plus RCB cross MVCB. Okay, this is just for your information, equation 2.30. So perhaps you can go and check it out. Okay, and HC is 0 for reasons which you should be knowing by now. Okay, so T is equal to half into MVC square is equal to TC. W dot will be equal to F dot VC is equal to Wi star. Okay, this implies that M moments about C is equal to the rate change of momentum about this point, and that is 0. Okay, so the equations of motion can be written as F into MAC into and MC is equal to 0. So this is equation 2.93. So this also means that the resultant, I haven't actually shown the point B over here, but B is somewhere over here. Okay, and this, it's outside the system. This is clearly RCB. Okay, now the resultant at C of the external forces is a single force Fr is equal to F is equal to MAC. Okay, so the CR will be equal to MC, the resultant couple moment will be equal to 0. Okay, let me show that with a diagram. So I want to draw a system which looks at least something like this. Okay, so it's the same system which we have seen before. You have the point C now, you have the equivalent as CR is equal to MC is equal to 0, and this is FR equal to F equal to MAC. Okay, show, because it's a moment, I should show it with this line. Okay. So this is how the resultant at C of the external force system is. This FR and CR over here. Okay. So if you have an arbitrary point, say B again, somewhere like this, the velocity is VB. Okay. And you have this line, say D. You have this line BD. In the direction E. Okay, so consider an arbitrary point P shown an arbitrary line BD in direction E. Actually, I should show it like this. Okay, in direction E. Then you can write that MB is equal to MC plus RCB cross F. Okay, and MC is 0, so this would be RCB cross MAC. Okay, from over here. And MB therefore can be written as RCB cross MAC. And MBD, which is the moment about a line, okay, that would be this RCB cross MAC and dotted with E. So we have learned this also before, the moment about a line. So you have to just take a dot product with the line. So this implies that MB is actually equal to 0. Okay, if the BC vector is parallel to AC, okay, then this cross product of RCB and AC would be equal to 0. So this is 2.95. And this implies the moment is 0 only about any point on the line of acceleration. AC through C. Okay, the moment is 0 only about any point on the line of acceleration vector AC through C. Okay, now we want to see whether this MB, so B over here seems to be an arbitrary point and we have found out the moment to be 0, but let's try to directly say that this is not 0 for just about any arbitrary point. Okay, so let's show that. Same body, C is the center of mass, acceleration of C, D is over, say here, t is over here, and ak, this is point k, this is acceleration of k, this is say g, this is ag. So I'm pointing out the directions of acceleration of all these points. Say you have a, this is the acceleration of a, and then you have b, acceleration of b is equal to 0. This also has vb. Say this has point e, acceleration of e. You have this point d, acceleration of d is equal to velocity of t. Both of them are 0. And you have this point h, which is fixed. So for a translator, we want to show or sort of argue that for a translating system, the moment is not 0 about any arbitrary point. MC is equal to MD is equal to ME is equal to MH is equal to Mg is equal to Mk is equal to 0. Okay, this is definitely all true, though Mk is not equal to H dot K. Okay, and Ma is not equal to 0. Mb is not equal to 0. Md is not equal to 0. Okay, Me is also not equal to 0, though Ma is equal to Ha dot, Mb is equal to Hb dot, okay, and Md is equal to Hd dot. So you can see that the moments about C, D, okay, have I shown E in this? Okay, there is also a E over here, which is, the idea is that they are all lying along the same line, okay, and they all have accelerations, okay, which are either 0, okay, or parallel to the line with the center of mass, okay, like satisfying this condition. So this is the reason, because so K, even if this is lying along this line which is joining the center of mass, like all other points, its acceleration is actually pointing in a direction which is different, ak, and hence you don't have the moment as 0. So this brings home the point that the for a translating system, the moment is not 0 about any arbitrary point, okay, it has to satisfy this condition. Okay, so You should now check for yourself that for a translating system, the impulse moment relations are the same as given in, say, an earlier section where we had discussed the impulse momentum. So let me just in earlier section on impulse momentum relations. This is written in red so that you can go and verify. You have to read that section again, put all this to use, okay, all this which we have discussed over here, and then you should be able to find that all those relations hold in this particular case for a translating system. So that's a very good thing, even if your system is not actually an inertial frame, okay, as long as it is translating with respect to an inertial frame, all those impulse momentum relations hold. So that's a very, very good thing for us. Okay. Now, since W dot is equal to W dot star, V star is equal to V, and T is equal to TC, okay, the work energy relations okay will be T dot is equal to W star, T2 minus T1 is equal to W of 1 to 2, T dot plus V dot is equal to W dot NC, T2 plus V2 minus T1 plus V1 equal to W NC 1 to 2. .96. Okay, and most of this we have just learned a few minutes ago. So if you have, say, a conservative system, T dot plus V dot is equal to 0, T2 plus V2 is equal to T1 plus V1, okay. So this is equation 2.96, and if you say have a system which consists of lot of connected translating subsystems, so the system is made up of lot of subsystems which are all translating, okay, then you can apply this equation to each one of those subsystems, okay. So that can be applied. So 2.96 can be applied individually to all the interconnected translating subsystems then add up relations for the whole system. Okay, so you know that something which was internal to the system will become an external force to the individual subsystem, so you have to consider all that separately. So let me just write down more explicitly these equations. Okay, so I want to say that T dot is equal to W dot internal plus external, T2 minus T1 is equal to W internal plus external 1 to 2, then T dot plus V dot internal plus external is equal to W dot NC, okay, non-conservative. So there will be too many subscripts, so let me just write NC over here. Okay, internal plus external, and then this equation can be written like T2 plus V internal plus external 2 minus T1 minus V internal plus external 1 is equal to WNC internal plus external 1 to 2. So you have conservative systems T dot plus V dot internal plus external is equal to 0. Okay, because there's all the non-conservative terms, this and this would become 0, and automatically this would imply that T2 plus V internal plus external 2 is equal to T1 plus V internal plus external 1. So if all internal forces are workless, okay, then 2.97 will reduce to 2.96. Okay, so 2.97 will reduce to 2.96 if all the internal forces of interaction are workless. So this is something which you should note. It's anyways visible clearly if you look at 2.97 to 2.96. Okay, so hold on. Let me write a couple of statements in red for you to figure out. The work energy relation is useful if the interconnected system has only 1 degree of freedom. Okay, You have the work energy relation in front of you for interconnected system. Okay, so why is it that the work energy relation is useful if the interconnected system has only 1 degree of freedom? Okay, and then the rate form is used to obtain acceleration. So that is something which is obvious, so I'm not separately writing out. Okay, so some of the examples, I mean, you can see the statement in red perhaps by this diagram. Let me just draw. Okay, so there's a pulley, a block, so you have these blocks which are connected like this. Let's see, this is 4, this is 3, all interconnected systems, and then you have 1 and 2. Okay, now if you separately sort of draw the free body diagram just to differentiate between the external and the internal forces, well, if this is a whole system, so now I want to write individual subsystems. So one will be, so I'm writing for 2, M2G, okay, and N2, then the force due to the string, then the friction mu2 N2. Okay, now write for 1, you may have M1G, this would be P1, this would be P2. Okay, this would be P1, this would be P2. Now you have to write for 3, let's write P2, M4G, M4G. Okay, and P3 is the tension in this string, N4, and friction would be like this. You should already know what's the assumed direction. Because of this velocity, we already know how friction should be acting. Okay, sorry, this is 4. Right now, 4 will not have a P3. It will have a P3 like this. Okay, and similarly for 2, sorry, this body 3, you will have a N3, you will have a mu3 N3, you will have a M3G, you will have a P2, you will have a P1. Okay, so the 1 degree of freedom system is there, and it's very useful to solve this problem using the work energy uh, which you have just learned. Okay, and the other statement clearly over here is that the rate form is used to obtain acceleration. For example, that what this means is that if you have the acceleration given, okay, then you would use the rate form, which is like something like this. Okay, and if the velocities are given, you can just write this one, use this one. So either of them work, okay, depending on what you need. So this system of interconnected bodies is important because you have to realize that if there is a machine, there are many parts of it which are interconnected to each other, and hence this becomes an extremely important sort of subject of discussion anywhere under any study. Okay, So there are you can have these three methods to approach a problem like this for several interconnected systems, several interconnected translating bodies. So in the example which we have just discussed, the diagram of which is visible to you, there is clearly a translation with respect to an inertial frame for all the bodies. Okay, for several interconnected translating bodies. So the first, as you know, is already the force is equal to MAC. Okay, MC is equal to 0. Okay, so you can have this as F equal to MAC. Okay, and you can write this F equal to MAC and MC is equal to 0 for individual bodies. So you can have the internal and external forces separately written. Now say you can have a second situation in which you may have this F equal to MAC for whole system. Okay, and the third one would be the having a resultant force on the center of mass. Okay, so all these three methods one can use to find the to solve this issue of translating interconnected bodies. Okay, so let's now learn about the dynamics of a rigid body with mass concentrated at C, the center of mass. So before, let me just sort of draw this. What do we want to do over here? We model a stiff body with mass predominantly confined to a small volume. As a rigid body with its mass m concentrated at its center of mass C. Okay, now let me draw that an example of this. This is a light rod. This is a torsional spring, okay, with its torsional stiffness Kt. Okay, and this is a mass point m. Okay, so over here you have a light rigid rod with a heavy bob. Okay, m is the mass, let's call it mass m at end. Okay, so this can be modeled as a rigid body with mass m concentrated at C, because the rod is light. Okay, the bob can be assumed to be a mass point. Okay, we have learned about what a mass point is, so it's a reasonable thing to do over here. But the only problem is the forces don't really act on C alone. So if you want to draw, say, the free body diagram, yes, the entire mass mg, this force is true, this dot is the center of mass. Okay, but over here you see, what is this constraint? It allows a rotation. It, first of all, let's apply the constraints. This point will be fixed over here both in the planar directions, hence it will have reaction force R1 and R2. Okay, secondly, it will also have a constrained motion for its rotation. Okay, so the rotation over here, this is a spring. Okay, so it's not a free rotation. Of course, it's not zero rotation, but it's also not free, and hence you would have a kt theta applied over it. Okay, for a given angle theta, this is O. So these are the reactions, and this is the situation. The entire load on this body does not really act at C. Okay, so this is the FBD, and theta equal to 0 is the undeformed spring. Okay. Now for this system, we can write the moment of momentum about the point C, which is the center of mass, as RCC cross MVCC to T. Okay, this is equal to 0, and MC would be equal to H dot C. This would automatically also be equal to 0, and F is equal to MAC. So the moment about point C would be equal to this. Okay. Now this is something which you should be very comfortable answering. If not, why is this moment of moment about C written like this? Okay. Okay, so if not, you should pause the video, figure it out, and only then move ahead. Okay, now the resultant of the external force system at C is a single force. If you want to draw, for example, the resultant, Fr is equal to F is equal to MAC. Okay, and for arbitrary point, that would have, sorry, arbitrary point B. I'm not shown B in the diagram, but it's an arbitrary point, so MB over here would be RCB cross FR. Okay. Now this would automatically mean that MB would be equal to RCB cross MAC. This is equation B. Okay. Now if you want to write the kinetic energy, that would be T equal to half mvc square equal to Tc. W dot is equal to F dot Vc plus mc dot omega. Okay, but mc is 0, so this would be just F dot Vc. Remember, F is the resultant force acting on the center of mass. Okay, and this is the rate of work done by external forces. So this is equation C. Now Tc dot is equal to W dot star. This implies that T dot is equal to W dot So this is the work energy relations which we have just discussed. Okay, because T is equal to Tc, hence this is equal to this. Okay. So this equations, if you see over here, are exactly the same as over here. Okay. So for a mass point, you have the exact same expressions as you had for a translating system. So that's what we conclude over here. Green, the equations A to D of a rigid body mass point. I hope you can see that this is clearly as a system deformable. Okay, I mean it's definitely changing as a system, but you are assuming you can model it like a rigid body mass point because the rod is light and rigid, so it can be assumed that its entire mass is at the center of mass C. Okay, so the equations A to D of a rigid body mass point are exactly the same as those for a translating system. Okay. The reason clearly is that I mean Hc is equal to 0 for a translating system. Okay, so omega is irrelevant. So both the cases Hc is equal to 0. I think you should have a vector sign over here. Okay, so that's where we can end our discussion on the dynamics of a rigid body with mass concentrated at the center of mass C, and perhaps the final topic which we can take up in this particular chapter on axioms and force system is the equation of motion C relative to a translating frame. Okay, so we have had many translating frames, and let's just finally write the equation of motion of the center of mass relative to a translating frame. So consider a frame T translating with constant acceleration at relative to an inertial frame. Okay, we have just discussed this. So the equation of motion of the center of mass of any system, okay, can be written as Fn plus Fmg. So Fn is the sum of all non-gravitational forces. Okay, so for equation of motion you require the external force, and one is definitely the force of gravity, and the other can be all the non-gravitational forces. So if you want to write the equation of motion, this would be Fn plus Fmg equal to Mac with respect to I equal to MAC with respect to I frame plus AT. Okay, so we have just written the acceleration of C with respect to the I frame as the acceleration of C in terms of the T frame. Okay, and obviously this acceleration of T is with respect to the I frame. So we don't really write this I frame all the time, but it's very clear over here. Let it be, but in the future I'll be dropping this I frame down. Okay, this means that Fn plus what is the force of gravity? Mge equal to MACT. Okay, where GE is equal to G minus AT. Okay, so this is okay, so I hope you can see what we have done. We have written this MAT, this particular term, and combined it with this G term. So that's how this has come up. Okay, so once this is done, so let this be called as equation 2.110. Okay, really shows how far we have come into this. This is the 110th equation of this particular chapter. Of course, we are only discussing the theoretical aspects of it. Okay, now this can be written as Fn plus Mge, apply dot it with a Vc in the translating frame on both sides. Okay, and this can be written as Vc in the translating frame dot Vc by T, or this can be written as d by dt half into m Vc of T whole square. Okay, now this particular term should be easily identifiable. Okay, that is the kinetic energy in terms of the center of mass. So this implies that T dot C in the T frame is equal to W dot star in the T frame. Okay, or T dot CT plus V dot star T equal to W dot star NC T. So we have broken down into conservative and non-conservative. The conservative one is equal to minus of V dot star. Okay, so this term is the rate of work done relative to T by what forces? Fn plus Mge. Okay, as if acting at C. W dot NCT, this particular term, is the rate of work done by non-conservative part of the forces, and W star T is the potential energy, V star T is the potential energy relative to T frame. Okay, and clearly it is due to the conservative forces, because you are writing the W star conservative as minus of V star conservative. Okay, this also is looking exactly like in the previous cases. So relative to T, which is a translating frame, okay, the equations of motion of C and the work energy relation are exactly of the same form as those relative to I, provided this force mg and its potential energy minus mg dot r are replaced by this equivalent mge and minus mge dot r. Okay, you can see that this sorry, where did it go? This one. Okay, other than that the equation is exactly the same. Okay,